Hey Phys 1 kids. In today's video on electrostatics, we're going to look at forces. Now, one of the things that's really interesting about electric forces is that they're very similar and yet different to gravitational forces. If you remember Newton's universal law of gravity, right, the force of gravity is the constant g, 6.67 times 10 to the negative 11th, times the quantity of the masses, mass 1 times mass 2, over the distance between them squared. So gravitational forces, right, are long-range forces. There's no contact. The Earth doesn't reach up and grab you when you jump. You just come right back down. The force is proportional to the mass, right? There's my equation. Larger masses have larger force. That's why we see the force when we're by some very large object. And force decreases with distance, and it's an inverse square law, distance squared. The one thing we're going to see that is different is that the force is attracted, right? You're always attracted to other masses. You're not repelled by them. For electric forces, the forces are also long-range forces. Remember that when we were playing with the electroscope and I brought the charged rod near it, it didn't need to touch it in order to force those leaves apart. So there doesn't have to be contact for an electric force to exist. One thing that's true about electric forces is that they're proportional to the amount of charge. The more charge I put on an object, the greater the force is. But the force also decreases with distance. The more I move away, the weaker that electric force gets. The one difference to so all those things are similar to gravitational forces. The one thing that's different is that electric forces are attractive like gravitational forces, but they're also repulsive. So it depends upon the sign of the charge. Now, the equation for calculating electric force for point charges, and that's all you'll have to worry about in this class, is given by Coulomb's law, which says that the electric force is the constant K, which is Coulomb's constant. The magnitude is 9 times 10 to the 9th, times the magnitude of the charge, or the product of the charges. Now, each charge in Coulomb's, you need to use the absolute value of the charge, so it doesn't matter if it's negative or positive. That determines the direction of the charge. But when you calculate it, use the absolute value of the charge. So don't put positives or negatives when you calculate the magnitude of the force. The distance, r, is the distance between the objects, and it's an inverse square law like the force of gravity. And of course, always use meters when you're calculating distances. Now, one thing that is true, and I put this right here, is that when I have two charges present, the force on one is equal to but opposite of the force on two. Think about how you calculate it, right? Both of those charges are in this calculation. So no matter which one I calculate it for, the equation's the same. And remember from the last slide of the force of gravity, wow, looks very similar, doesn't it? Except gravity is masses and electric force is about charge. Now, the direction of an electric force is along a line that connects the charges. So when you're drawing vectors, they should either be pointing at the charge or away from the charge. And so if it's an attractive force, so if the charges are opposite, the arrows, the force arrows would point towards each other. If they're repulsive, the force arrows will point away like this. So along the line that connects a charge, you're going to draw two repulsive arrows away, right? This is, if we call this charge 1 and charge 2, this is the force on 1 by 2. Right? It's pushing one away. It's exerting a force of repulsion. And over here, this is the force on 2 by charge 1. If they were opposite charges, right, then it would be attractive. So they want to get towards each other. So the force vectors would point towards each other. Opposites attract, likes repel. What about the magnitude of the force if we had unequal charges? Would those forces be equal? Would the force on my +4 charge be the same as the force on my -2 charge? I mean, the +4 has a bigger charge. Well, no, they're still equal and opposite. Remember Coulomb's law, if I asked you to calculate the force on the positive charge by the negative charge, right, you'd go K, Q, +4 -2 over R squared. If I asked you to calculate the charge that the +4 exerts on the -2, you'd do the exact same calculation. So equal but opposite forces. It's a Newton third law pair. So you're going to get trick questions like this all the time. What is the magnitude that this huge magnitude charge exerts on this itty bitty charge? And you're going to want to say the forces are different, but they're not. They're equal and opposite. So don't get fooled. Let's do a calculation. So I want you to pause the video and see if you can calculate the force and find the direction, right? Force is a vector of the charge, of the force that this positive charge of positive 3 microcoulomb exerts on this negative 5 microcoulomb charge. Now, micro, if you don't remember, micro is times 10 to the negative 6. Charges are small, so we usually deal in micro and nano. Well, if you did this right, here's we have a distance of 2 meters apart, so there's my distance. And here's our K, 9 times 10 to the 9th. Here's the one charge. Notice that we're not using the negative in the calculation, so 5 times 10 to the negative 6. And here's 3 times 10 to the negative 6. And make sure you're working in meters for distance. So we need to convert that 2 millimeters into either 0.002 meters or 2 times 10 to the negative 3rd. And don't forget to square it. So if you do this correct, you should get 3.38 times 10 to the 4th newtons. And the force that the positive charge exerts on the negative charge, right, is in this direction. So it's to the right. That's the force this charge exerts on that charge. Remember, only use the sign of the charge when to determine the force direction. Never use it in the calculation. So earlier we talked about the similarities and differences between electric force and gravitational forces, but let's now look at the difference between magnitudes. Now, if I have a typical pith ball, and what a pith ball is just an insulating sphere that I coat with a conductive surface. And if I have 2 of these and I charge them both the same way and they get the same sign of charge, they're going to exert forces and repel each other. So they will, oh, that pith ball stuck at me. Now they're going to exert forces of repulsion and be pushed some distance r apart. So the electric force, right, is our Coulomb's constant K times Q1, Q2 over R squared. Now, a typical charge on a pith ball would be 10 nanocoulombs, and let's say they both have the same charge. Well, then we're going to take our 9 times 10 to the 9th and multiply by 10 nanocoulombs, so that's times 10 to the negative 9th, squared, right? There's 2 of them, they have the same charge, so it's the same as if we just square it. Divided by our distance, but in meters, so 0.03 squared. So if we plug that into our calculator, we're going to find out that the force is pretty small, 0.001 newtons. So not that impressive, but these are teeny tiny little pith balls. But what about the gravitational force? The gravitational force is that gravitational constant times m1 times m2 over r squared. Now the gravitational constant is small, right? It's 6.67 times 10 to the negative 11th. And our mass is really small, right? That's in milligrams, and you need to be in kilograms, right? So if we go to kilograms, that would be 100 times 10 to the negative 6th, right? We've got to go over, that gets us to grams, and then another 3 to get us to kilograms. And of course, we got to square that. They have the same mass, right? Multiplying the same number by itself is like squaring divided by 0.03 squared. Well, if we do this math, we're going to find out that it's 7.4 times 10 to the negative 16th newtons. Teeny tiny force. So a lot of times when we're dealing with electric forces, we just ignore the gravitational force because on very small masses, it's just really not that significant. Now, why are neutral objects attracted to charged objects? You know what? Let's take a look at a video because that's pretty cool. Go to video. One really cool phenomena is that charged objects can attract neutral objects, whether they're conductors or insulators. So here I have a soda can, and here's my plastic rod. Right now my plastic rod's not charged, so I'm going to touch it and make sure there's no charge on it. And notice that there's no interaction with my conductor, the metal soda can, or with this paper insulator. But now I'm going to charge this by rubbing it with a rabbit fur, charging it by friction. The more I do this, the more electrons I add. Now if I bring it by the soda can, oh, there goes the soda can. If I bring it by the insulators, look at it picks up the little papers. So why does that happen? Well, what happens when we bring a charged object by a neutral object, we get charge polarization. Remember charge polarization from the last video? It's when positive and negative charges separate from each other. So I get attractive forces. When I get this charge polarization, the opposite charge is close to the charged object. And so that exerts an attractive force, and I have a repulsive force pushing on the like charges which get farther away. So for example, here's a conductor, right? The soda can was the conductor. If I bring a negatively charged object towards it, like I did with the rod, I'm going to force the electrons over to the far side. They're going to get as far away as possible. That leaves this with a net positive charge, and because of that, right, the distance here, my R value here, is a lot less than my R value here, which means I get an attractive force that is higher in magnitude than the repulsive force. And so I get attraction. So the soda can rolled towards the rod. The same thing happened with the paper, but the paper is an insulator. So in this case, I didn't have the electrons completely moving. What I did is I had some torquing of molecules and moving of electron clouds, but I still get the same result. I still get a net positive charge on the surface and a net negative charge on the other surface, and I get the attractive force is closer, right? Those opposite charges are closer, so I get a net force of attraction. And if that force is higher than the force of gravity, those pieces of paper jump. All right, one more question. If I have an uncharged conducting sphere and it's hung next to a charged sphere, so let's say this is my neutral sphere and this is my charged sphere. What happens if I release this sphere? So I let it just swing. Will nothing happen? Will it be attracted to the charged sphere, or will it be repelled? Well, remember the soda can? It gets attracted to the charged sphere. By having that charged object there, we get that charge polarization. So the negative charge attracts the positive and repels the negative. So I guess maybe this is a negative charge, and then this would be negative, and this side would be positive. So this is actually going to swing over here. So the thing is physically going to move over here. So the positive charge is closer, so I'm going to get a force that's stronger for attraction than I do for repulsion. Did you get it right? All right.